In the previous lesson, we have learned that an object, by virtue of its position, may store energy. This energy can readily be transformed into other forms of energy, such as energy in motion, which we already know as kinetic energy, or other forms like chemical, electrical, and even heat. This type of energy is what we call the object's potential energy. It is called potential energy since there is a potential for work to be done against the object if it will be allowed to. As of now, you can easily understand that work is done when lifting objects and climbing up the stairs. This is work done against gravitational force. This type of potential energy is called gravitational potential energy or GPE. The amount of gravitational potential energy possessed by a system is equal to the amount of work done against gravity in lifting or pulling down an object. This is also the energy associated with the state of separation between two objects that attract each other by gravitational force. To quantify gravitational potential energy, when the object is lifted at a constant speed, the force required to lift it is equal to its weight, mg. Again, our general definition for work is it is done on an object equal to the applied force multiplied by the distance traveled. From this, we can say that the work done on an object against a gravity is a function of its weight and relative position or height. The higher the object is at any given point in time in reference to a point, the higher the object's potential energy. In equation, we can describe this as U sub gravity is equal to mgy, where U is the gravitational potential energy, m is the mass of the object, g is the gravitational acceleration constant, and y is the height. When we studied work, we learned that the work done on an object can be positive or negative, which depends on whether the force applied is along its displacement or not. Let us see if you can still remember which of the following statements best describe the relationship between work and displacement. That is correct. If the force applied is along the displacement of the object, the work done is positive. If it is against the displacement, it is negative. The total work done on an object due to the gravitational force is equal to the change in its gravitational potential energy. In equation, we can express this as W sub total is equal to delta U gravity. Let us substitute the value of gravitational potential energy from our previous equation, where U is equal to mgy. There is a change in elevation and therefore a change in gravitational potential energy. Therefore, we will treat y as y sub 2 minus y sub 1. The final equation would be total work is equal to mg times y sub 2 minus y sub 1. To better understand this concept, take a look at this illustration. A body moves downward and the only force acting on it is the gravitational force or its weight. The work done by the gravitational force is positive since the force and the displacement are in the same direction. Of course, we can expect a negative value for the change in potential energy since final height is less than the initial height, right? The same analysis can be made in the next figure, where a body is moving upward. Of course, it won't move upward unless there is an external force applied into it. What can we say also in the work done by gravity? That is correct. The work done by gravity alone is negative, as it acts in the opposite direction of the displacement. Again, taking into consideration the equation above, what can we expect about the value of potential energy? Very good. It is positive since final elevation is greater than initial elevation. Here's a table to summarize the sign convention for work and energy due to gravity. If the object is moving upward, the work done by gravity is negative since they are acting on opposite direction. But the gravitational potential energy increases because there is an increase in height. Likewise, when the displacement is downward, the work done by gravity is positive because the object and the force is acting on the same direction. The gravitational potential energy will decrease because there is also a decrease in height. Before I end this lecture, take a look at these three different scenarios of lifting a ball. Take time to review. which has the greatest potential energy. As what we have learned in this lecture, potential energy is a function only of the object's mass and elevation, which means that it does not matter how the object is elevated or dropped, as long as they are at the same height, their systems have the same potential energy. If you are going to look back at the definitions or scenarios that I provided to you, you may notice that when gravitational potential energy is referred to, it is always of the system and not of the body. This is because potential energy is not a property of the object, but a property of the interaction between the object and gravity or the Earth itself. In this set of illustrations, your reference point is the ground, and if you lift the object from the ground, the potential energy increases because the elevation or the height increases. Therefore, since we have the same value for the height across all situations, all of these three methods have the same amount of potential energy. We will have mathematical examples of gravitational potential energy in the next video. But that is all for this lecture. I am Gilmar De Castro, and see you in the next video.